Dear guests, so back in 2005, there was a DARPA challenge on autonomous vehicles, and there was a robot Tommy who took part in it. It has to pass 200, I believe 200 kilometers, but we love Tommy not for that. We love Tommy because it crashed into the wall in the middle of the desert at the speed of 100 kilometers per hour. And our next speaker, Alexey Voropaev, will tell us what modern vehicles do to prevent that. So please welcome.
I'm head of perception system team at Evocargo, and my team teaches trucks to see the world. Today I tell you how we implemented and continues to create and improve the perception system. Big companies often have enclosed territories like this one, like warehouses, production sites, ports, and so on. And they need to transport within such territories. Conventional solution is to maintain a fleet of small cargo light trucks, as well as the driver workforce. But conventional does not mean efficient. And aim of a cargo company is to implement efficient logistics service by using autonomous light trucks. We are working only on enclosed territories. Such territories are small, well cleaned, with road markings and good light. And what's more important, they have speed limit. Sun conditions good for smooth integration of truly autonomous trucks in customers' fleet. Evocargo has created autonomous electric truck for enclosed territories. It drives less by design. It doesn't even have a cabin for controlled driver. One charge is enough to drive 2,000 kilometers with 1.5 tons of cargo. And our maximum speed is limited by 25 kilometers per hour. It's equipped with cameras, lidars, and ultrasonic sensors, like any other self-driving car. The history of Evocargo trucks goes back to 2017. Back then, our engineers started building first model using camera-based technologies. Really, if we look at this image from the front camera of our truck, the task looks easy. We just need two neural networks, one for detection and another one for segmentation. We use for detection YOLO V5, used for, and for segmentation we used PSP.NET. Detection we use to predict behavior of objects on the scene, and segmentation we use to find drivable area to safely drive our truck. Using this information and precise map of a territory in combination with centimeter level localization, the truck can drive safely. It's not a problem that images and results of neural networks are flat, because almost everywhere enclosed territories are built on a flat ground without hills. So we can just estimate the distance to objects by using simple geometry properties. And actually this image, this one, was cherry-picked, as in many articles about computer vision. The reality looks like this. The storm grate on the road is interpreted like an obstacle, and the car is not sure what it sees. And there is no much space to drive this obstacle around, so car will stop emergently. It's okay from the safety point of view, but it's bad from the business point of view. The logistic manager will not be happy if the cargo carriers often make emergency stops, right? Let's look more examples of detection issues. These two images, my favorite. In the left one, the truck successfully detected drowned guy on the road and stopped every time on this point of the road. In the right image, the truck sees a dog there. Just power on imagination, and you will see it in the wet spot. Yeah? This kind of Rorschach test for self-driving. And let's see how we can improve perception quality. One of the trivial way to increase the perception quality is to increase model size. Here we trained several models with the same architecture, but with different size. Plot shows us grow quality during training process. As you can see, the largest model with XL index grows much faster than the smallest one. It's a classical tricks in data science. We just exchange quality for performance. And as you may guess, a larger model requires more powerful GPU. And it's the problem. In our project, we are limited by design requirements. We need a certified industrial embedded computer like this one, and it must work in difficult environment and weather conditions 24/7. At the same time, we need to process images 10 times per second with a latency as low as possible. Adoption for mass production and economical consideration are also important. So we choose NVIDIA 1660, and on this GPU, our baseline implementation of YOLO and PSP.NET worked only with 4 FPS. So we need to find a way to speed up the inference time, as well as increase perception quality. Unfortunately, the NVIDIA 1660 doesn't have tensor cores, so we can't use half precision or integer quantization. One more way to speed up inference of two networks is to join them into a single one. If you look at the architecture of both YOLO and PSP.NET, they will find common parts. To put it simple, the backbone takes input and produces abstract features at different scales. The neck analyzes these features from different scales at the same time to find an object independently of its scale. And finally, head just produces the final expected result. The idea of multi-head networks is to use common backbone and neck to solve different tasks. This is, on the image, the structure of the YOLO-P model. It has common backbone and neck for 3 heads. And each head solves its own task. One for drivable area segmentation, one for line segmentation, and one for detection. As a result, we save a lot of computing resources. Later, I will show you the final performance result, but now let's talk a little bit about quality. Let's consider a segmentation task, since it's more important for us. One way is to use special loss function. Conventional loss function is for segmentation is a uniform sum of error in each pixel of image. It means that all pixels are equally important for the network. But it is not true for the self-driving. Errors at the bottom of the image are more important because they can cause emergency stop, while points on the top are not very important, since they are far from the car. Yeah? And so we can gradually weight points from up to down and increase importance of the points below. And here is the results. Left it's before and after its network trained with this special loss. You see that holes near the car disappear. That's great. Our logistic manager is happy now. And here is the video of results. It's a test drive of our car. You see image from front camera and 2 images from side cameras. On top, it's detection results, and you see not all cars are detected. But at the bottom, you see that segmentation, especially on the front camera, are very good. And this quality is good and fast enough to for the truck to drive. Yeah, we still have some problems on side cameras, but they are not so important as a front camera because we want to hit the wall. And here is the table with performance and quality metrics. As you can see, we significantly speed up our inference time from about 50 milliseconds per one frame to 19 milliseconds. And with little degradation in detection quality, you see that detection quality drops, and boost in segmentation quality because we used special loss. We are still working on improvement of this network. Detection quality drop is not a big issue because this drop usually becomes with objects that are far away from our car, and we have a lot of time for reaction. Boosting segmentation for us is more important. Also, we can increase performance. Also, we increase performance even more by replacing original PyTorch inference engine with NVIDIA Tensor RT engine. It's a specialized engine from NVIDIA, and you see the difference in performance time. In some case, it's almost 2 times here. It requires extra coding effort, but result is worth it. Even more speed up we can get if we use half precision or to use integer quantization. But unfortunately, it's not our case because NVIDIA 6016. We are looking for a new computation unit. Brand new NVIDIA Orin looks good for us, but it's quite fresh. I hope we will try it next year. And one more way to speed up is to use new architectures. Yellow P version 2 looks pretty promising for us. It's very fresh architecture, and we don't try it to use, but it's very fast. So, for further performance boost, we need to collect more training data. There are a lot of tricks how to do it efficiently, and I can make a separate lecture about that. But today I will show you only one of them. For image annotation, we use CWAT tool by Intel. It's a great tool with a lot of instruments to simplify annotation process. But our assessors still need to do a lot of manual work to annotate the picture, especially for segmentation. Yeah, we need to select all these points. And we found the way to train a drivable area segmentation network without annotation at all. We apply a Lidar sensor to do that. A Lidar is a specialized distance measure sensor that's used in self-driving. It measures distance using reflection time of laser beams. The LiDAR on our vehicle sends 32 laser rays simultaneously, scanning 70 degrees of vertical space in the following pattern. And this LiDAR is called rotational LiDAR because inside there is a part which rotates 10 times per second. So one rotation gives us about 60,000 points of surrounding space. And we set up 2 LiDARs on top to achieve circular view around the car. Yeah? As a result, we get such image of surrounding space. It's 3-dimensional scene top view formed by points from LiDAR. It's called point cloud. And it can be difficult to understand this image first time. At the center of the image, there is our truck. Green is the road, and red are walls of buildings and parked cars. The LiDAR is a physical presence sensor. It means that if there is an obstacle on the ray path, that we know exactly distance to this obstacle. Yeah? As a result, the algorithm for drivable area segmentation can be much more simple and robust than in the camera case. In this image, you see segmentation result using our algorithm without neural networks. So we can drive using combination of cameras and lidars. And even better, we can train camera neural network using lidar data. To do that, we need to backproject road points on the image and implement special loss function. On the left image, you see the segmentation results achieved by traditional conventional neural network. Yeah, it's good. And on the right side, you see the segmentation from neural network trained only on lidar data. You see that results the same, but what is important to understand is that this neural network trained without human annotation at all. It gives us a lot of opportunity and saves a lot of money. For example, we can fine-tune a separate model for each location where we work and obtaining great quality. Here is more interesting example at night. You see that our LiDAR training network on the right works very well and greatly outperforms the classical one. And this boost is for free in terms of data annotation that's very expensive. We will publish a scientific paper soon about this algorithm with details of our algorithm. And of course, we can use LiDAR data for detection in the same way. Here you see the same scene, but from another perspective. Using specialized neural network that is called center point, we can detect cars, it's blue boxes, and peoples, it's green one, in 3 dimensions. And after that, we can train image-based neural network in the same way. Of course, here we need manual annotation because it's almost impossible to implement classical algorithm for detection on LiDAR clouds. But the amount of annotation to train such network for LiDAR cloud, it's much less than for image detection. However, LiDAR has its own limitation. I will not talk about cost and durability today. For perception, one of the major disadvantages is sensitivity to snow, rain, fog, and so on. In the video, you see snow in LiDAR rays. It looks like white noise on this video again. These points interfere with our algorithm and greatly reduce perception quality. Fortunately, we can apply a simple algorithm based on nearest neighbor search. And when we enable the filter, the white noise disappears, and you see green clouds of real obstacles. You see the algorithm works well enough. But it works only for medium snow, not for heavy rain. Another problem is density of point clouds. As you see here, our LiDAR see well enough at 35 meter max, and the black car is in pink box is located on this distance. On the right, you see this car in different projections, and you can see that our 2-megapixel camera sees this car well enough, but LiDARs touches this car only by 3 rays. Yeah, it's not very well, and it's main limitation for distance. Unfortunately, this problem can be solved only by using more expensive LiDARs, and since we are in production, it's not our way. I believe that in case of enclosed territories, we can solve problem of perception using only cameras system, but we need some more time. And now we want to create a model that combines both lidars and cameras, images for detection and segmentation. Finally, I want to tell a few words about our further research direction. First one is creation of camera-based model that detects objects directly in 3D on molecular images. It's a complex problem since the network should to estimate distance to objects only using semantic information. However, we are working on this and can show you some intermediate results here. On the right, this scene is bird eye view, and green is ground truth, and red is our detections. And you can see that these detections is very well. Of course, there are some problems. Here, for example, we do not detect bus ahead of us, and we don't see people on the right side. Yeah, but in justification, I will say that this scene is really complex, and it's night and with bad weather, and I don't see the pedestrian too. What we to do? We can create a joint network that combines lidars and cameras, for example. And finally, I want to tell you a few words about another sensor that's widely used in self-driving. It's radar. It also provides, like LiDAR, physical presence of the objects, but it's not afraid of snow and less expensive. This sensor is widely used in automotive industry and for cruise control and collision avoidance. In the video, you see bird eye view of LiDAR cloud and radar cloud at the same time. Run again. Actually, it's I playing with my dog here. And small points are from LiDAR to understand what is scene about. And large and rare points are provided by radar. Of course, we can't use this information to create radar-only detection for self-driving, because low density, because these points are two-dimensional, and some materials are invisible in radar, like plastic. Yeah, but we can create a network that combines image and radar information. Radar will provide presence information and distance, exact distance information, and network from image take information about orientation of object and its class. Yeah, clear. Okay, that's all I wanted to tell you. I hope I have shown you that creation of truly autonomous trucks with some restriction is solvable task for today, even without expensive hardware. And I also hope this lecture was interesting for you, and thanks for your attention, and I'm up for your question.
Thank you very much. Don't forget to rate the talk, and we have at least one question here, please.
Oh, hi. Have you considered augmenting neural network not only with LiDAR and not only with radar, but for example with infrared cameras and infrared projecting lamps, because you are able to install infrared projecting lamps on the truck, because you basically could install anything on it, and use infrared cameras to augment neural network for bad weather conditions, for night conditions, etc., etc.
Yeah, it's possible to equip truck with infrared cameras, but there are two problems with that. The first one, these cameras are very expensive, even more than LiDAR. It's very, very expensive. But we are creating production systems with production site, and we try to minimize cost of our car. It's first point. The second one is that this camera also sensitive for snow, for rain, and for dirt on the glass, and for the same problems as a usual camera. So as a result, the boost in quality which you will receive is not so much to pay for this camera.
Any more questions? Yes, we have even two.
Several years ago, I came across a story about Rotterdam seaport, and they also use autonomous trucks, but there are no cameras, no lidars, nothing on perception, because they have special marks on the road, and trucks orient themselves using these marks on the road to transport the sea containers. So if you control fully the territory where the truck is operating, why do you need such a difficult perception system if you control the territory and you can be sure no one enters it and only autonomous trucks are there? So why do you need such difficult perception if you can simply use special road marks or special emitters on stable obstacles just to inform that there is no way here?
Yeah, I saw such solutions for indoor system. For example, I made a fleet of small sorting robots that works in the same way, but you can't run this car in territories where there are another people on another car, where there are another activity. I mean this territory only for these robots. It's the first problem. And the second problem is that there are very different territories. There are territories where a lot of snow, and the snow every time beyond the Arctic Cycle, for example. There are territories where we can just put these markers, and these markers is significantly degraded over time if there is another activity on this place. And as a result, yeah, for some cases it's possible, but not in just the general case.
And another question in front.
Yeah, thanks a lot for the presentation. I want to ask about why you're trying to use only monocular vision for detection of 3D boxes of the objects, because you have a lidar, you have radar, you have several cameras. Why do not use two cameras or double check? There are a lot of CNNs that trying to use information from one for teaching another part.
There are two questions here. The first one, why we don't want to use LiDAR in combination with camera, yeah? Why we want to create monocular 3D detection? It's because LiDAR is expensive. LiDAR don't work well in bad weather conditions. LiDAR have small durability and lifetime in comparison to cameras, and so there are a lot of problems with LiDARs actually. And there is no such problems with cameras. And why we don't use two cameras and stereo vision? Actually, the first perception system for this truck was with stereo cameras, but with these cameras also there is a lot of problems. If we use classical algorithm for stereo vision, we find as a result a lot of problems that can be eliminated. For example, we see some obstacle where there is no obstacle, yeah, and car just stop. As a result, we need to pass these images to some neural network. As a result, we increase difficulty of task, we need larger networks and so on. And if we see that this task is solvable only on monocular images, it's significantly better. It's faster, it's cheaper, and it's more robust. I hope I explained you, no? No? Okay. We can continue this discussion after the lecture.
Any more questions? Yes, please.
As I understand, to create a performance system, you need not only to detect visual objects, but to understand physics of these objects. You have to predict where they are moving and have basic understanding of the physics. That means if I see this chair and then in next moment I don't see it for some reason, I will not lost this presence in my mind.
Mhm. Actually, there is such system in self-driving. It's called prediction system. It works after perception, and the system predicts trajectories of objects that we have detected. It's why we need not only segmentation, we also need detection to find this object for which we want to predict behavior. But as we work in enclosed territories, the speed of us and speed of other objects is slow, and for us this system is quite simple. It's worked well, and it's not covered by my lecture.
We have a question online, and let me spell it. Have you considered possibility to use external territory surveillance cameras and sensors for better truck localization and obstacle detection?
External, no, because it's difficult to install on enclosed territories. It's easy to do on some concrete territory, but if we're creating a general solution, we don't do it. Maybe only for localization, but it's topic of research.
Okay, thank you. And the question here.
By the way, have you invested in like performance improvements regarding like latency issues, video processing, for example, process frames in parallel on multiple GPU units or something? I'm just asking because I've heard a talk from, I don't know, from someone from Tesla. They're heavily investing in in performance issues, in reducing latency, in reducing signal path from the camera to the GPU unit, on reducing, on improving performance of the deployed neural networks and stuff. I just want to know if you have any such measures.
Yeah, we are working on this problem, and actually we have a dedicated engineering team who is working on the latency, on some performance optimization and so on, and my team mostly working on performance of neural network inference. And of course there is more ways than I talked about. For example, we can use batching and process few images at the same time, and it's also increase performance but reduce latency, for example. And in Tesla, there is a lot of resources. They even create own GPU, and it's another topic. One more question?
One more question to the left, please.
Thank you for the interesting talk. When you talk about like the lack of GPU resources on your visual, do you talk about like only resources like spent on perception, or do you like compete with other teams on spending these GPU resources?
Yeah, we actually compete because there are more systems in the self-driving. There is a localization system who consume resources of both CPU and GPU. There is planning and control systems that also consumes mostly CPU resources. And our task is to process images at 10 FPS. And if we can't do it, it's reason for emergency stop.
Any more questions? I have one. Consider how many trucks do you have on the site simultaneously?
I'm not sure that I can disclose this. It about.
Okay, no. If it at least two of them, can we merge them for them to share information between them and share resources?
In theory, it's possible, yes, but it's not a topic of our today research.
Okay, thank you. So we have a gift for the best question, I remind you. Anyone else wants to take a part in this? No? Okay, so it's up to you to decide who got the best question for your
I think it's that guy in second row.
in the second row.
Yeah.
Yes. This one. So, thank you. Thank you, Alexey. Thank you, everyone.
Thank you very much.
Enjoy the after party. Enjoy the networking. See you later.